Early in your education, you may have come in contact with the roadmap of atoms, the periodic table, the subject of this lesson. Is this a table of atoms or of elements? The term atom in everyday usage refers to a tiny particle too small to see, whereas the term element is used to describe a sample that might contain a vast number of atoms. The gold in a ring or bar is a beautiful element, composed only of gold atoms. The element carbon is composed only of carbon atoms, and so forth. So we call this the periodic table of the elements. We see that the remarkable sequence of 118 elements occupies 7 rows. Only hydrogen and helium occupy the first row. Notice the 6th and 7th rows have subsets, which are called the inner transition metals. I'll not comment further on transition metals except to say they are enormously important to the proliferating devices of today's world. Each element is designated by its atomic symbol, H for hydrogen, He for helium, and so on. The symbols are mainly the first letters of the element's name. For example, the atomic symbol for carbon is C, and for neon is Ne. In some cases, the symbol refers to the atom's Latin name, like Au for gold, aurum, and Fe for iron, ferrum. An element is defined by the number of protons in the atom. The number of protons in an atom is the atomic number. Hydrogen, the simplest element, has 1 proton, so the atomic number of hydrogen is 1. Helium with 2 protons is atomic number 2, and so forth. Any atom with 26 protons in the nucleus is by definition an iron atom. Elements in the periodic table are arranged in order of increasing atomic number, listed above each atomic symbol. Listed below each symbol is the element's atomic mass. The standard unit of atomic mass is based on the mass of the most common form of carbon, which is arbitrarily given the value of exactly 12. So the atomic mass unit is 1/12 the mass of this common atom. Hence the element carbon-12 is defined to have an atomic mass of exactly 12.0000. But you see the carbon listed as 12.011. Why not exactly 12? This brings us to isotopes, atoms with differing numbers of neutrons in the nucleus. Most carbon has 6 neutrons accompanying its 6 protons. But some carbon atoms have more than 6 neutrons. These are isotopes of carbon, notably carbon-13 and carbon-14. Ordinary carbon is about 99% carbon-12, with 1% carbon-13 and even less carbon-14, which causes the average atomic mass to be a little more than 12. Note that the atomic mass for hydrogen is 1.0079. Why not exactly 1? This is mostly because the definition of atomic mass is based on carbon, not hydrogen. Isotopes also play a small role. Although most hydrogen consists of a single proton, some hydrogen atoms include a neutron, and fewer still, 2 neutrons. These are hydrogen isotopes. Hydrogen 1 alone has a mass of 1.0078. When the atomic masses of hydrogen's other isotopes are averaged by isotopic abundance on Earth's surface, the atomic mass for hydrogen is 1.0079. The number below iron is 55.845, which is an average mass of its several isotopes, 2 of which we see here. All elements have a variety of isotopes. Average atomic masses are uncertain for the heaviest elements, so they are listed as integers. When we study nuclear physics, we'll learn how mass is related to energy and how Einstein's celebrated equation, E equals mc squared, plays a major role in atomic masses. We'll later learn that protons and neutrons, when bound together, effectively have less mass than when they are separated. More about that down the road. Whizzing around the nucleus of every atom are tiny electrically charged electrons. In an electrically neutral atom, there are as many electrons as protons. For example, a gold atom, with its 79 protons, has 79 electrons. I hope in school you weren't asked to memorize the periodic table. If you did, you'd have learned nothing of scientific value. The physicist Richard Feynman is famous for saying that if you memorized the names of all the birds, you'd know nothing about birds themselves. We don't just memorize names, we go beyond knowing the names of things and study their properties, their interactions, and how their behavior enables prediction of new knowledge. Memorization is often the first step to knowledge, but as said, if it's the only step, then that knowledge is of questionable value. So what do we learn from the periodic table? Why is it a table and not a list? Because the table displays regularities. Within each row, the elements show a regular progression of properties. One such property, and an important characteristic of atoms, is size. We depict the relative sizes of atoms with this view of the periodic table. Notice how going from lithium, number 3, to neon, number 10, atoms get smaller. But they jump to a larger size at sodium, number 11, at the beginning of the next row. And regularities in size persist into the heavy elements. Notice that the xenon atom, with its 54 electrons, is smaller than the rubidium atom with its 37 electrons. Why? Because all 54 of those protons in xenon pull with much greater force on the electrons than do the 37 protons in the rubidium nucleus. The electrons of proton-rich atoms are simply pulled closer. Another characteristic of atoms is their electrons' arrangement. Electrons behave as though they are arranged in a series of shells about the nucleus. Those with only a single shell are hydrogen and helium. Those with 2 shells occupy the second row of the table. Those with 3 shells occupy the third row, and so on. I'm not showing the other 4 rows here. But here's a 3-dimensional idealized rendition of an atom with 7 shells. If you can read the numbers, they tell the maximum number of electrons a particular shell can accommodate. Chemists are fiercely interested in the electrons of the outer shell. These electron configurations account for the bonding between atoms to form molecules, the temperatures of melting and freezing, electrical and magnetic properties of materials, and the taste, feel, appearance, and color of substances. This lesson barely touches on the periodic table. There is so much more that can be learned from this wonderful roadmap of the elements. If you take a course in chemistry, you'll spend a lot of time exploring the periodic table. I want to leave you with 2 questions. Which contributes more to an atom's mass, electrons or protons? Which contributes more to an atom's size, electrons or protons? Until next time, good energy.